Hello everyone. We are starting to discuss the problems that were proposed in the Junior League. Let's start with the problem number 1 of the second section. So this was the first problem. There were two congruent squares as it was shown on the figure, and it was necessary to prove that the sum of two red segments is equal to the length of the third one. The simplest, I think, explanation was the following, that you should take these. So first of all, these three segments are parallel to each other because of the symmetry of this figure with respect to the for example, bisector of this angle. So if I draw here bisector, then I will get that the figure is symmetric, and thus it means that all these red lines are perpendicular to this bisector, and thus they are parallel. And in this, if you made this observation, then you could just construct here a parallelogram with such side and find that this is the side of the square, of course, so it is equal to this one, and at the same time this side is equal to this one and parallel. So these sides are equal and pairwise parallel. And thus we see that these two triangles are equal. So they could be actually, you could just shift one of them and get the other. So this could be one of the approaches. But they just have equal sides which are parallel, so this is enough. And thus you have that this segment is equal to this part of the bigger one, and this segment is equal to this part. And that's it. But as I see, almost everyone who was submitting solutions solved this problem, so I think that there was no problems with this. Let us switch to the next one. The next one was algebra about increasing sequence, and it was somehow about some sequence with inequality. So it's very similar to such kind of problems about functions. So it's like functional equation, or in this case functional inequality. And one of the main ideas behind such problems is to try to test some concrete m's and n's in this inequality. And in this case, of course, we could take for example n equal to 1, and we will get that am plus a1, which is equal to 2024, is greater than equal than am plus 1 plus m minus 1. So m minus 1 will be just here without absolute value. So we see this, and of course we could write this only in case when this condition is satisfied. So we should assume that m plus 1 is smaller than k, smaller or equal than k. And thus we get the inequality that 2024 is greater than am plus 1 minus am plus m minus 1. And this guy is at least 1, since we have strictly increasing sequence, and thus this is greater than m. And we get the estimate for m, and since m is not bigger than 2024, and it could actually we could place m equal to 1, etc., k minus 1, we get that then k cannot be too big also. So k is smaller than 2025. And this is actually the answer. We should provide some example here. And of course, since we see such kind of inequality, one of the basic ideas here is to test some simple sequence. And the simplest sequence in this case is just arithmetic progression with difference 1. So we could start with 2024, then write 2025, etc. 2024 plus 2024. And here we'll get exactly 2025 numbers. So a n in this case is 2023 plus n, I think. So this is the answer. And and this sequence satisfies the inequality and all the conditions. It could be checked just simply by putting this formula into this inequality. So I should check that 2023 plus m plus 2023 plus n is greater than or equal than 2023 plus m plus n plus absolute value of m minus n. And yes, since we know that m is not too big, we could see that this inequality is true for all m's and n's in the range which we expect. So this is the basic idea of this problem. If you have any questions about this problem, please ask in chat. If no, then we could move forward here. And third problem was about two girls, April and June. And here there are different approaches for solving this problem. And one of the approaches is to find how we could block April at some point. So of course we would like to force April to get some big number in such a way that she cannot at some point calculate, subtract something or add something in such a way that she will give a number out of the range. And our idea should be, yes, to increase the number of April by each step. And there are different strategies. I know, for example, one of the strategy for June is the following: is to tell April a number which is divisible actually by all numbers in the range from 1 to 999. So for example, always say, for example, 999 factorial, the product of all these numbers. Then if April has number n, then the greatest common divisor of n and 999 factorial will be n, and thus since April can't subtract this n, she should add this, and thus she has to make new number which is equal to n. So she will need to multiply her number by 2 at each step. So and this will be the strategy of June, and thus after 10 steps, April should get the number which is greater than 124, and this is impossible. So the only possibility is to have not more than 9 steps at this time. So there is some question here. No, there are no questions, just about Saveli's camera. Okay, so in this case, June could act in such a way that there will be not more than 10 steps. Yes, so on the 10th step, June will have no possibility to do something. And so this is one of the possible strategies. Another possible strategy is to say some numbers which relates to the powers of 2. For example, on the first step, to say 2, and if April has number which is divisible by 2, then she will get the number which is divisible by 2. If if April has number n which is divisible by 2, then she will make n minus 2 or n plus 2. If n is not divisible by 2, then she will get n minus 1 or n plus 1, and both these numbers will be divisible by 2 in this case. So these numbers are divisible by 2 and these numbers are divisible by 2. So after our first step, the number which has April should be divisible by 2. And then we will switch to next step and say 4. And in this case, all even numbers could be divided into groups, divisible by 4 and not divisible by 4. And if we have at this point a number divisible by 4, then we will get one of the numbers n minus 4 and n plus 4, which is divisible by 4. And if n is not divisible by 4, then it has remainder 2, and the greatest common divisor of 4 and our n is 2. So in this case, n is of the form, for example, 4k plus 2, and the greatest common divisor of this number and 4 is 2, and we will get either number 4k or 4k plus 4, and they will be both divisible by 4. And so on, increasing the power of 2 on each step. We playing on the place of June will get that after each step, April will has number which is divisible on the next power of 2. So and step by step, at the step number 10, we will get that the number should be divisible by 124, and this is impossible. So this number is out of range. And this is the other strategy for the June, how to finish the game in 10 steps. And smart people here would say that actually it is not necessary to increase the power of 2. You could just say 2024. So on each step, the greatest common divisor that we were calculating here is the same as the greatest common divisor with 2024. So we just calculate the number of 2's which is inside our number and give this as an answer and add or subtract from the initial number. And then the power of 2 will increase step by step, and at the end of the day we will get that the power is very big. So there is some question in the yes, 124, yes, 100, yes, 24. It's very natural to ask for the year. Yes, thank you. So this is the strategy for June. To win in 10 steps. And what is the strategy for April not to lose in 9 steps? It's very simple. Strategy for April is to take number 1. Yes, and then on each step, the worst thing that she should do is to double this number. And since 2 to the power 9 is 512, it is smaller, it is the number in the range, so we could proceed with 9 steps in the range. So this is the strategy. So I think that this is a very, very beautiful problem, and I liked it a lot. And I think that, yes, there were a lot of teams who solved the problems. I hope that you enjoyed it. If you have any questions about this problem, you could ask in chat. And we could switch to the next one. So the problem number 4 is about the graph. And I think that this problem is quite difficult. So it is necessary to perform several steps. And these steps all of them maybe not so hard, but in total, this makes this problem quite challenging, and I see that not so quite many teams solve this problem, but not too much as previous problems. So let us examine this problem carefully. So let's start with the following. So we will construct a graph. So we have students as vertices, and friendship, of course, is edges of the graph. So we have 35 vertices. And have quite a lot of friendships there. So each student's the degree of each vertex is between 25 and 30. And first thing that we should understand that it is not possible that all vertices have degree 25. So there exists vertices of degree at least 26. This is due to so-called handshake lemma. So we know that actually the number of the vertices of the graph with the odd degree should be even. And the reason for this is because if we try to calculate the number of edges, we should sum up all the degrees and divide it by 2. So this sum should be even. And it can be that all 35 vertices have degree 25 because this product will be odd, and it's not possible. So we have the vertex of degree 26, and if max is correct, then there are no let me denote this vertex by V. So we have degree 26 here, and if max is correct, that at most 5 of them of degree 25, at most 5 of them of degree 26, and so on. So we have 5 25s, 5 26, and so on, 5 29s, and this is still less than 26. So we have only 25 possibilities of such kind, and thus we conclude that there exist vertices of degree 30. So at first step we conclude that from handshaking lemma there exists vertices of degree 26, but now using the conditions of the problem, we understand that if max is correct, then there exists a vertex of degree 30 by pigeonhole principle. So now we take this vertex, let's say W, and it has degree 30, and again we assume that max is correct. If max is correct, then among these 30 vertices, exactly 5 of 25s, 5 of 26, and 5 of 30. So this will give us exactly 30 vertices and no other possibilities if max is correct. But in this case, we find out that we have actually 6 vertices of 30. So again, we start with one vertex of 26, conclude that there is one vertex of 30, and the next step that there are 6 vertices of degree 30. So we now have 6 vertices of degree 30. I draw 7 for some reason. So yes, and I just would like to say that there exists some vertex that is connected with all of these 6. And this will be the contradiction, because if max is correct, then any 6 vertices, there are no 6 vertices with the same power which connected to one vertex. So why is this true? each vertex of degree 30 is not connected with 4 vertices. So we have only 4 vertices which is not connected to this one, 4 vertices which is not connected to this one, and so on. So we have 24 vertices which is not connected to one of these 6, at most 24 vertices. And of course the 6 vertices, this vertices itself, so we can't assume one of them be this one. So, but this is still smaller than 35 students. So we have 4 vertices which is not satisfied us from each of these, so it will give us 24, and these 6 vertices we also exclude from our considerations, and at least 5 vertices will exist actually which connect to all of these 30s. And since we find such guy which is a friend of these 6, then we find out that Max is not correct. So this is the solution. So it has, from my point of view, several steps. Most of these steps are natural, but it's hard to pass all of them. Do you have any questions about this problem? If no, I think that we can go to the next problem. This problem number 5. This is number theory. From my point of view, it is maybe simpler than the problem number 4, and I think that yes, there are much more submissions here. Not much more, but more than in problem number 4 from my point of view. So okay, what kind of observations we can make here? First observation is the following, that if we consider the product of consecutive numbers, for example, of 4 consecutive numbers, then a plus 2, a plus 3, then this number will be divisible by 4. So if you compute the product of the consecutive numbers, it will have this divisor, but this number is not divisible by 4. This means that k cannot be greater than 3, and thus we have only 2 possibilities, k equal 2 and k equal 3. So how could we proceed with these 2 cases? I think that there are different approaches here. So for this case, for example, we could consider that this stuff is equal to some a times a plus 1. And then just try to solve this as a quadratic equation with respect to a. So, and since we know that this should have integer solution, it means that the discriminant of this quadratic equation should be itself perfect square. So what is the discriminant of this quadratic equation if we're considering it as a quadratic equation of a? So it should be something like 1 plus 4 times 36 to the power n minus 6. And we see that actually this is 4 times 36 to the power n minus 23. And this is quite a big square itself. So this is 2 times 6 to the power n square. And we know that the difference between two squares, k square minus k minus 1 square, is 2k minus 1. So the distance to the closest square to this one is something like 2 times 2 times 6 to the power n minus 1. And if n is big, is greater than 1, then we get that this is much more than 23. So it's not enough to subtract 23 here to reach to the previous perfect square. And this is the reason why this case is not possible. So the discriminant cannot be perfect square in this case. What about k equal to 3? So in this case, we also could just write in this way, but I will use a little bit different. I will write a minus 1, a minus, oh, I think that I even will write a minus 1, a minus 2, a minus 3, in such a way that this minus 6 will disappear. So this will be a cubed minus 6a square plus something a. It will be 6 plus 2 plus 3. So it will be 11a minus 6. So this 6 will disappear here. And we find out that this 36 to the power n can be represented as a product of two guys. And here we know that a should be big enough, I think. Yes, so a is bigger than 1, surely. Yes. I think that it's even bigger than 3, even bigger than 4. And it's smaller than a square minus 6a plus 11. Yes, I think that it's quite easy to check that a is actually a should be quite big here. So it's this product is bigger than 36 to the power 2, so this is bigger than this guy, and this is quite big number. So this means that actually a is bigger than something, I don't know, than 5. And this will give you that this stuff is bigger than this one. But also you could find that these two numbers are coprime. So the greatest common divisor of a and a square minus 6a plus 11, we could divide this by a, the first part here. So this is the same as greatest common divisor of a and 11. And a, of course, should be coprime with 11 since it is a divisor of 36 to the power n. So this is 1. So these two numbers has no common divisors. And since they both bigger than 1 and have this inequality between them, we have the only possibility that a is 4 to the power n. And a square minus 6a plus 11 should be 9 to the power n. So this is the only representation in as a product of two coprime numbers. And this is impossible again because we just could put this a here and get that here it will be 4 to the power 2n minus 6 4 to the power n plus 11 should be equal to 9 to the power n. But this guy is 16 to the power n, and this number is bigger than 9 to the power n. For n, I don't know, bigger than 3, I think. So even if we subtract here this number, it doesn't compensate the difference between the power of 16 and power of 9. So it cannot be true. A little bit in another approach for this k equal to 3 could be performed observing the reminders on division on 7, for example, or I think maybe other models offer also okay. So it's possible in some cases just to check some reminders. So if you have any questions, then please you could ask in the chat. If no, then we could move forward. Oh, this is a very beautiful problem, I think. I love this problem very much, but I think that it is a hard problem. Let me check. Only 2 teams solve this problem. So it's, I think, one of the most interesting problems, actually, I think. And the idea here is a little bit simplify this stuff. So here we have a quite long list of perfect squares, but it's not clear how to work with this, and the idea is try to simplify this problem and simplify the situation. So let's say that b is a good number if the integer part of b is a perfect square. So here we have that all these numbers are good numbers, and we would like to understand that a itself is a good number. And the main lemma here I would like to prove is the following, that if b square, b cube, and b to the power 4 are good, then b itself is good. So you see that this is very close to the idea of the problem itself, but we simplify it a little bit, considering the smaller number of good powers of b. And how could we proceed with this? Idea is the following. So let me squeeze b between 2 integer numbers. So it's greater or equal than n and smaller than n plus 1. It means that the integer part of b is n. So what does it mean? It means that b square is actually greater than n square and smaller than n plus 1 square. But we know that b square is good. So the only possibility for this is to be b square actually squeezed not between these numbers, but between these numbers. So this means that b square is good, and since b square has the only square below the b square is n square, we will get this inequality. But then we could square this inequality and get that b to the power 4 is greater than n to the power 4 and smaller than n squared plus 1 to the power 4, to the power 2. And again, we know that this number is good, and it is squeezed between two consecutive squares, perfect squares, and thus it should be that n to the power 4 is smaller than b to the power 4 and smaller than n to the power 4 plus 1. So, okay, actually at this point we squeezed b between very close numbers. So we are almost done, but we would like to understand to use the property of b cube here also. So what should we write here? We should understand the following, that b is bigger than n, then b cube is bigger than n cube, and thus I could write the following, that b cube is smaller than n to the power 4 plus 1 divided by b. So I write this inequality in this way. This is smaller or equal than n to the power 4 plus 1 divided by n. I use this inequality. I decrease the denominator here. This is n to the power 3 plus 1 over n. And of course, this is smaller than n cubed plus 1. And bigger than n cubed. So here I think that I could write the strict inequality here, because we have here strict inequality. No, here it is not strict, but here we have strict inequality, and thus we have that the integer part of b cube is n cube, and this is a perfect square so we now know that n cube is a perfect square, then it means that n itself is a perfect square. And that's it, we proved the lemma, because n is integer part of b. So we prove that it should be a perfect square. So this is the main ideas behind this lemma. And now we just have to use this lemma to prove the main problem. So we know that this, etc., this number are good, and among these numbers we have these guys. All of them are good. Then using lemma we get that this guy is good. Now we could use the same for these. They are good, thus 8 to the power 9 is good. And so on. We could go down from 8 to the power 10 to the rest and get that A is good. At each step, we'll get that the second, third, and fourth power of the next power we're considering, they are all in the list of the good numbers. And thus, we could go down by step and get the answer. So, are there any questions about this problem? Maybe something is necessary to repeat. I lost the chat somewhere. Yeah, it's here. What about strictness of proof? Number 5. I don't understand the question here. Maybe you could elaborate a little bit your question. What do you mean by strictness? Maybe you mean that sometimes I'm saying that the number is big or not. I think that you could cover these details yourself. But of course, we were assuming that you are providing strict proofs during your presentations. So, yeah. This proof sometimes I was not given exact estimates, but we, of course, during the defenses of the solutions, we were expecting this from you. But now I just would like to save some time for all of us and skip some details. So the problem number 7 is the geometry problem, and at first glance maybe it looks not very beautiful, and it's not maybe so clear how to solve this problem, and it looks not very natural, but I like this problem anyway, not because I know the author very well, but it's because there is an idea behind this problem. So it's I think very good situation when you have such kind of ideas. And what is the main idea here is the following, that the right triangle is quite interesting one, and let us maybe discuss some background stuff. So, for example, I think that all of you know the following formula for the area of a triangle. So if you have a triangle and you have in radius of the triangle, then the area of the triangle is semi-perimeter of the triangle times r. So this is a plus b plus c over 2 times r. At the same time, actually, there are the same formulas for the area with usage of x circles. So if we consider the x circle of triangle, and this radius is RA, then the area of the triangle will be RA times P minus A. So how can I prove this? It can be proved in the same way as usual. So I could consider 3 triangles. This one, it has altitude equal to RA and the base equal to AC. So this area is B times RA over 2. This triangle also has altitude equal to RA and the base equal to C. So this area is equal to C times RA over 2. And if we sum these areas, it will not give us area of ABC, so we have to subtract this one. And this one is A times RA over 2. So the answer will be B plus C minus A RA over 2. So this is the formula. And thus you have a very beautiful bunch of equations. So RP is equal to RA times P minus A times RB times P minus B, RC times P minus C. And actually these formulas lead to a lot of other beautiful formulas in triangles. But what is the relation to our case? The relation is the following, that if you have right triangle, then for example, this in radius R is equal to the segment, to the tangent from the right angle. In our case, right angle is C. So in this case, we see that R is equal to semi-perimeter minus C. At the same time, if I consider RC, I will also get a square here with sides RC, and I will get that the pole perimeter of semi-perimeter of the triangle is RC. And the same will be for two others. So RA will be equal to P minus B, and RB will be equal to P minus A. So in these beautiful formulas, actually we will get another stuff. So we could replace this radius by semi-perimeters, or vice versa. We could replace semi-perimeters by radius in this case. So for example, we could write that R times RC is RA times RB. So this could be get for the right triangle, and vice versa. You could get that P times P minus C is equal P minus A times P minus B. And actually, if you could skip the first part of the solution and just try to understand this formula, and this formula is equivalent to the Pythagorean identity for the right angle triangle. So you could just open the brackets here and find that A square plus B square is equal to C square and nothing else here. So, but how could we express this identity in another way, in more geometric way? We could think that this stuff is power of vertex with respect to some circle. So, for example, I look at a triangle and considering in circle here and x circle here and x circle here. And maybe not x circle here, but and x circle here. Yes. And if this vertex is C, this is A and this is B, then we will get that this stuff is P minus A, this stuff is P minus B, this stuff is P minus C, and the rest, for example, this one is P. So, and we see that if we're considering these 4 points, this 1, 2, 3, and 4, they will lie on a circle if and only if we have this identity. And this is true only for right angled triangle. And this is what is done here in our case, actually. So we could check that actually this circle is passing through all points of tangency. So these points are points of tangency of the x circle of the triangle. So here I could draw this circle. Here also it will be x circle, and here x circles. So, and if it is true, then of course there are no problem to prove that ax equal to yb, because all of them equal to these guys and to the in radius of the triangle. So the idea that these, for example, these 4 points belong to a circle is behind this problem. So just a calculation for of such kind for the right triangle shows that these 4 points live on a circle. At the same time, these points also should lie on a circle. And this, at the same time, these 4 points should lie on a circle. So you see that actually the idea of the author of this problem is that this identity gives us information about the tangency points, that all of them lie on some circle, which is true only for right angled triangle. So now how could we proceed to the problem? So first of all, we should prove that all tangency points such lie on a circle. One of these for 4 points, I proved it using this identity, and I leave to you the rest. So the rest is the following. So you should check in the same way that these 4 points lie on a circle. It is actually the same identity. And one more thing is this, that these 4 points lie on a circle. This is the tangency points. So you should calculate here the power of the points through the point C. You will find at the end of the day that 6 tangency points lie on a circle. And now the only thing that it is necessary to show that these points P and Q are the same as the tangency points. So the construction of our points P and Q in our problem will provide us the tangency points. So let me try to explain this part. So in this case, we have our right angled triangle, and we make the following construction in our situation. So we take the tangency point of the in circle and construct the point E such that the angle here is 45 degrees. And one of the main considerations from my point of view is that this means that the point I is the orthocenter of AEB. So this angle AIB is 90 plus 90 over 2. So it's the angle between bisectors of angles A and B. And this could be calculated by this formula, is 135 degrees. And this angle is 180 minus 45. So we have in triangle point on the altitude such that this angle is alpha and this angle is 180 minus alpha. So this point is unique on the altitude on the same side, and this is the orthocenter of the triangle. So actually these lines AE and BE, they are orthogonal to these bisectors. And so this is almost enough for finding that these P and Q are the points of tangency of the X circles. So how could we do this here? So I forgot this part a little bit. So what we would like to prove now, that we have right angled triangle we construct here the altitude and the in-center and the point such that this in-center is the orthocenter of triangle. And then we project this to the sides of triangle, and we would like to understand that these points are the tangency points of the x circles. So, for example, x circle here is tangent to this point. Okay, honestly speaking, I'm not sure that I remember correctly the details here, but I think that you could recover this from the part that I already discussed. So I think that it's just possible to check that this line is going through the x center, and maybe just make some simple calculations here in terms of Pythagoras theorem. So this will be enough. So how the solution will look like after that. So again, the first observation that in right angle triangle, such kind of points are lying on the same circle. So it could be done via such calculation. So we get that in right angle triangle there are 6 points lying on a circle. And then we would just like to understand that our construction here leads to the tangency points of the x circles, and this will mean that this circle PQD is exactly the circle that we already discussed. And since it's exactly the same circle, it means that points x and y are tangency points of the x circles also, and thus AX is equal to BY and actually equal to the in radius. And in addition, you will get also beautiful fact that this AD is equal to this one. So yes, sorry for not finishing this problem. Let me switch to the last one and cover this problem. Let me look how much solutions were submitted. Only one team I see that solved this problem. From my point of view, this problem is complicated in the statement, but not very hard if you already solved such kind of problems where you have to estimate some kind of information. So the answer is the following, that actually the maximum value of n is 2 to the power k minus 1. So n plus 2 is 2 to the power k plus 1. And in total, there are 2 to the power k plus 1 coins. So let us discuss how to make the algorithm in this case. The lower bound algorithm for such a number. If you have 2 to the power k plus 1 coins, we can select 2 to the power k coins, any subset of 2 to the power k coins from this to the power k plus 1. And we understand after testing that either on this set will be more fake coins than the normal ones, or in the rest, because we have more fake coins than real coins. In one of two groups there will be more coins, more fake coins. And if we get the positive answer from the tester, we know that in these groups fake coins more than the real ones. Or if we do not get such kind of answer from the tester, then we know then in the rest there are more coins. And thus we will get, after one check, we will get 2 to the power k coins such that more than half of them are fake. And then we just will go down using the induction. So we will again split it into two halves, check one of these half, and understand in which half there are more fake coins than real ones. And after k tests, we will get the group of 2 coins where fake coins more than real ones, and the only possibility is 2 fake coins. So this will be the answer. So this is the algorithm. So now we should explain why it is not possible to do this for the greater n. So for n greater than 2 to the power k minus 1, it is not possible to find fake coins. And in this case, there is a quite usual thing. So let us suppose that we have more than 2 to the power k plus 1 coins. And we know that at least 2 to the power k of them are real. And we considering our algorithm, and so we choose some group of coins, test it, and get the answer. We get one of the 2 answers, yes or no. Then we choose another group of coins, test it, and get again one of 2 answers. And thus we have a tree of possible scenarios of our testing. And at the end of the day, after k tests, we get 2 to the power k possibilities, 2 to the power k results. And if our algorithm works, we will get 2 to the power k pairs of fake coins. I will write here in commas. So if our algorithm is good, then in all such scenarios we will we should identify the pair of coins. But we could for all these pairs, take one coin and say that that this coin and make this coin real. So mark this coin as real. And so we will get some 2 to the power k number of real coins, and all rest we will define as fake coins. And in this case, it means that any of the scenarios will give us in the last on the last step the pair with the one coin is real. So I said something wrong. So we have 2 to the power k pairs of coins at the end, and we take one coin from each of the pair, and mark it real. So we will get not more than 2 to the power k real coins, and say that all others are fake. And for this group of 2 to the power k coins, for this distribution of the real coins, our algorithm will not work, because it will, on each scenario, will give one real coin in the pair. So this is the reason why this algorithm cannot satisfy us in case when we have too many real coins. So this is, I think, quite usual explanation why some algorithms with testing coins doesn't work.